Hello everyone, welcome back to my another reinforcement learning tutorial, and this tutorial will be about agents beyond DeepQ network, as you can see already from this image. Up to this moment, we covered most popular tutorials related to DeepQ network, so-called value-based reinforcement learning algorithms and deep reinforcement learning. DeepQ learning networks are relatively simple. To their credit, not only DeepQNs are comparatively simple, but there are many other deep reinforcement learning agents that also make efficient use of their training samples that are available to them. That said, DeepQ network agents do have drawbacks. If the possible number of state action pairs is relatively large in a given environment, then the Q function can become extremely complicated, and so it becomes intractable to estimate the optimal Q value. Even in situations where finding Q is computationally tractable, DQNs are not great at exploring relative to some other approaches, and so a DeepQ network might not work properly. So even if DeepQNs are sample efficient, they aren't applicable to solving all problems. To wrap up deep reinforcement learning, I am introducing you the types of agents beyond DeepQ network. The main categories of deep reinforcement learning are value optimization, imitation learning, model optimization, and policy optimization, as you can see from this image. So, value optimization include DeepQ network agents that and their derivatives, for example, double DeepQ network, dueling DeepQ network, as well as other types of agents that solve reinforcement learning problems by optimizing value functions, including Q-value functions. Imitation learning agents in this category, for example, behavior cloning and conditional imitation learning algorithms, are designed to mimic behaviors that are taught to them through demonstration, by, for example, showing them how to do some kind of task, for example, pick and place the boxes. I thought imitation learning is a fascinating approach. Its range of applications is relatively small, and I will not discuss it further. Model optimization agents in this category learn to predict future states based on state and action at a given time step. An example of one such algorithm is Monte Carlo tree search. You can Google it if you want. And the last one is policy optimization agents, and they learn policies directly. That is, they directly learn the policy function P, and I'll cover these tutorials further. So, policy gradient is so-called reinforced algorithm. In DeepQ network, to choose which action to take in each state, we take the action with the highest Q value, maximum expected future reward at each state. As a consequence, in value-based learning, a policy exists only because of these action value estimates. So in this tutorial, I will cover a tutorial where we will learn a policy-based reinforcement learning technique called policy gradient. I already said that reinforcement learning agent main goal is to learn some policy function P that maps the state space to the action space. With DeepQ network, and indeed with any other value optimization agent, P is learned indirectly by estimating a value function such as the optimal Q value. With policy optimization agents, P is learned directly instead. It means that we directly try to optimize our policy function P without worrying about a value function. We'll directly select an action without a value function. Policy gradient algorithms, which can perform gradient ascent on P directly, are exemplified by a particularly well-known reinforcement learning algorithm called reinforce. The advantage of policy gradient algorithms like reinforce is that they are likely to converge on an optimal solution, so they are more widely applicable than value optimization algorithms like DeepQ network. The trade-off is that policy gradients have low consistency. They have higher variance in their performance relative to value optimization approaches like DeepQ network. And so, policy gradient tend to require a larger number of training samples. So a policy can be either deterministic or stochastic. A deterministic policy is policy that maps state to an action. You give in a state and the function turns an action to take. So deterministic policies are used in deterministic environments. These are environments where the action taken determine the outcome. There is no uncertainty. For instance, when we play chess and you move your pawn from a2 to a3, you're sure that your pawn will move to a3. On the other hand, a stochastic policy outputs a probability distribution over actions. It means that instead of being sure of acting, for instance left, there is a probability we'll take a different one action. The stochastic policy is used when the environment is uncertain. This process is called a partially observable Markov decision process. You can, of course, Google it and read about it more. Let's talk about advantages. The problem with value-based method is that they can have a big oscillation while training. This is because the choice of action might change dramatically for an arbitrary small change in the estimated action value. On the other hand, with policy gradient, we just follow the gradient to find the best parameters. We have a smooth update of our policy at each step. Because we follow the gradient to find the best parameters, we are guaranteed to converge on a local maximum or global maximum, as you can see from this image. The second advantage is that policy gradients are more effective in high-dimensional action spaces or when using continuous actions. The problem with DeepQ learning is that their predictions assign a maximum expected future reward for each possible action at each time step. But what if we have an infinite possible of actions? And let's take a simple example with a self-driving car. In each state we can have a near infinite choices of actions. For example, tuning the wheel 50 degrees, 20 degrees, 24 degrees, 50, I don't know, 70 degrees, it doesn't matter. But there might be an infinite amount of actions. We'll need to output a Q-value for each of these possible actions. On the other hand, in policy-based methods, we just adjust the parameters directly. Agent will start to understand what the maximum will be rather than computing the maximum directly at every step. Here's an example. Policy gradient simply goes right while DeepQ learning is trying to calculate all these Q values. So that's quite simple example. And the third advantage is that policy gradient can learn a stochastic policy while value functions can't. This has two consequences. One of these is that we don't need to implement an exploitation trade-off. A stochastic policy allows our agent to explore the state space without always taking the same action. This is because it outputs a probability distribution over actions. Consequently, it handles the exploitation trade-off without hard coding it. We also get rid of the problem of perceptual aliasing. Perceptual aliasing is when we have two states that seem to be or actually are the same but need different actions. For example, consider the game rock, paper, scissors, a deterministic policy. For example, playing on the rock can be easily exploited, so a stochastic policy tends to perform much better. Also, policy gradient has some disadvantages. Naturally, policy gradients have one big disadvantage. A lot of the time they converge on a local maximum rather on the global optimum. Another disadvantage of policy-based methods is that they generally take longer to converge, and evaluating the policy is time-consuming. Instead of DeepQ learning, which always tries to reach the maximum, policy gradients converge slower. Step by step, they can take longer to train. Regardless of these pitfalls, policy gradients tend to perform better than value-based reinforcement learning agents at complex tasks. In fact, many of the advancements in reinforcement learning, beating humans at complex games such as Dota, use techniques based on policy gradients, as we'll see in my coming tutorials. In simple terms, policy is the mindset of agent. The agent sees the current situation, state, and chooses to choose an action or multiple actions. So we define a policy as a function of state that outputs some actions. So it was a quite long tutorial, and it's usually hard to understand everything with plain text. So I will do this with basic Pong example, and I will implement it in Keras. Differently from my previous tutorials, I will try Pong deterministic v4 environment and Pong v0. Pong deterministic is easier to learn, so if our model will be able to learn this simpler environment, we'll try Pong v0. You might ask, why it's simple? It is the same Pong game. Actually, the deterministic game gives us all game frames, while Pong v0 gives us every fourth frame. It means it is 4 times faster, so it's much harder to learn playing it. So I will use my previous DQN network tutorial. I will modify the code to the policy gradient. You will see that it's not that hard. I already copied the code, so I'll just need to open it with another application, Sublime. And this is my previous tutorial code. I will be simply modifying this code to work as policy gradient. So mostly what I will do, I will remove a lot of code. So I will start with DQ. We don't need this. We don't need prioritized experience replay memory. And here we used convolutional networks. Right now I will comment these. We are not using them anymore because, well, it will be easier to train our model without convolutional networks, and I will just simply use a dense layer of one layer that we could use also convolutional networks if you want. I will leave it here, but I will just comment this code. Comment. You can uncomment it and use as convolutional networks. I will just need to remove all these functions, and our model will be model equal to model input x input, and output will be, and I will compile it. I will call it actor, and then I will use actor compile, actor compile, return action. We don't need a summary anymore, we don't use it. And optimize. Loss will be categorical cross entropy because we'll use our softmax now, and cut the recall cross and draw central. And optimizer will be RMS prop with learning rate of learning rate, and here I will just add a learning rate as input instead of the dwelling. Input shape. Oh yeah, I will use ELU, not a ReLU anymore, because it works better. And if you might ask me why, you can Google it, that it's better to use ELU instead of ReLU. And I'm removing these 2 lines. So right now we have actor, simply we have actor. Inputs as X inputs and outputs X. Yeah, it should be fine, that we can move forward. And now I will call it policy gradient agent instead of DQN. And here also I will need to delete a lot of code. I won't use seed action size, we will use a custom action size. Episodes, I will insert here a cell max average, and this will be a minus 21.0. This is specific for phone, so because there's a minimum score is minus 21, I can remove, I think, these lines, instantiate memory, and I can create a cell scores, cell episodes, and self.average equal to following episodes, batch size, DQN. We don't need all of this. Self batch, like that. Yeah, I will leave this here, and I will change self model name. Oh, I already had this, so okay, I can remove this. And here I will add one more line, so I will call it self path, and it will be my policy gradient algorithm, and I will format it as self environment name, and self learning rate. And I think we don't have this parameter yet, so I will add this somewhere here, and it will be 0.0001 probably, something like that. Model name, yes, we don't need update model steps anymore. I'll leave the same row calls remember steps. State size I leave, image memory I'll leave, and say self model I'll write self actor now, and instead of learning I'll write self learning rate. And target model, we don't need it, we don't have a target model. In policy gradient, self action size, yeah, everything is okay. The target model, we don't need this anymore. Define what I removed, I removed remember function, the target model, self remember. Yeah, it will change drastically, so I don't need a next state and done parameters. And experience, sorry, I will remove simply everything. So I will write self states append state, and I will copy this, and I'll create an actions and self rewards, and I think we don't have following memory, we need to create it. So right now I will write a action one hot, and we are creating one hot action from our cell action size, just like that. And we are adding an action one hot is equal action equal to 1. This is, we in the one hot we write which action we took, and this one we append to our actions, just like that. And now I will need to create a memory we don't have, and this will be self states, self actions, self rewards equal to nothing probably. I created a remember function. We can move to my action function. Actually, I'll remove everything here, and I'll write a prediction will be equal to self actor, and predict, and we would like to predict a state. So simply predict a state and need to write like, because there's prediction is a list in a list and we just like to squeeze it, and action will be equal to numpy random choice if I write it correct, and self action size, and sp we write a prediction and turn on action, just like that. And what's mostly changes our replay function, so I just also can remove everything we have here except self model fit probably. Okay, I remove it, and here I'll write that first take my states, and this is numpy stock self.states, and I do the same with my actions self actions. This simply I am reshaping them array into well, actually it's hard to explain, but there's a list simply and I need to stack it to a numpy array. This is the simplest way without any for loops. So actions, actually I already can do an actor fit, and I use states. Also I use states, then I use actions, and actually what I would need to do are sample weights equal to some kind of rewards, but now I will try to explain this at the end of this tutorial because this will be much easier to understand, and I will show you a graphs to understand it very good, everything in details. So this is reward, but in Pong there is rewards are a lot of zeros, sometimes -1 and sometimes +1 with rewards. So we need to use a discounted reward. For this purpose we'll use a discounted reward function, and this will be self discount rewards and self.rewards, and instead of rewards I will use a discounted rewards, and I will simply create here a new function that I will call this will be easier for me, def act, I mean discount, define discount rewards self and rewards word, and within we, so I will need to use return rewards. This is just for now. I will make modifications here. So we can write that we, for sample weight, we use a discounted rewards epochs, and verbose means we don't want to print our training results every training epoch. So that's it with a simple policy gradient function. We can move to our self load module, and this will be my actor name and self model load model actor name, and I will use on compile equal to false. This is needed because we'll use a custom loss function, if not now so in future, so it's better to have it here. It's like that. And what's wrong here with this define function? Not sure. Oh, I understood. Just like that, actor name, and for define save I'll use simply, I don't need this, but self model save, and I will use self.model name and plus we'll save it as type 5 model. So now we need to modify our lot model, and I need to remove a lot of these, so we don't use this DQ network stuff anymore. And save figure. I'll save figure a little differently, so I'll need to just write self.path. If you remember, we wrote this at the beginning, and it will be always the same name, except OS error pass, and we don't need this anymore. Self average -1, everything is fine here. And now, instead of plotting it every episode, I'll write it is if string episode of -2 is equal to, this means that we hit 100. This is much faster than writing some kind of number divided by 100. So I'll just writing this way, and yeah, I'll just do it like this. So we'll do our plotting just every 100 training episodes. It's good for us. It's quite enough. And now we can move to image show function. Now instead of card poll, I will use self model name. Everything is quite the same as before. I need to modify a get image, so I am not using render here anymore. We don't want to do that. Sorry. And I'll use the same cropping and converting to RGB structure. So, but I would like to use black and white, so I would like to add here a few lines. So it will be frame RGB, and here will be also frame RGB less than 100 will be equal to 0, and frame RGB more, sorry, simpler to copy, more or equal than 100 will be 255, just like that. And everything is the same, so we use our reset. I think we don't need to change it, and also step also the same. So I think we are ready to move to our run function here. So right now we won't use a max average here because we added it to our initialization function. So here we'll use a different structure of done score and saving. This takes less space on my code, like that. Decide step, we don't need this anymore, so while not. And everything's quite the same, except here if average, and here already have a self max average, self saves, everything is quite the same. And here I need to self save, we don't need this here. Oh, we don't need this explore probability also. Decide step we don't use. Next step done, we don't use this also. I use score and saving, I removed. And the target model also we don't need. Train model, yeah, we can leave this train model. And explore probability and remove, and episode also remove. So save, yeah, I think everything is removed here actually, and it should be probably ready for training. There might be errors because I'm doing it quite fast and I'm not wasting a lot of time to think what I'm doing wrong or not. Yeah, I think everything is quite okay. So force gradient agent here, might be later it will be with different names, so I'll just moving this, and we'll use a run function, and instead of Pong I would like to use a deterministic Pong, as I said. So it's called some kind of Pong deterministic before, and it should probably work. We'll build system 5.3. Okay, so my first error. Model action size. Give me a moment, I'll need to think about it. So yeah, I don't have an action size. I removed it. This was my mistake. So I'll write a self action size, and before it was written that self environment action space and just like that. So it should be fine now. Let's build it again. Action space, and yeah, it should be a dot. Act missing one requirement size step. Okay, size step, we don't need this. Build. Instead, A and pi must have same size. Yeah, here comes the problems. Okay, let's see what we have friendly here. Prediction. Yeah, let me check everything again. State action reward. Yeah, I think here I'm missing to restart our memory. So I'll write it here within replay function. Agent run action self act. So give me a moment, I will try to find this. So I think I know what is the problem, and let's try to run this again. And problem might be in our model that I forgot to add one more layer. So it's action, to calculate an action. So we need to add a dense layer similar as we did here. And here instead of 512 should be an action space. Action space, and we'll use same activation. No, we'll use our softmax max instead of VLU, and H uniform. As an input will be our X, and for output we'll use an X. So, but this is not the only mistake here, because there's a replay, and I thought that it might not work while there's zeros in our reward system. So for temporarily I will remove this, and let's check how it works now. And if it's working, I'll try to convert this on my GPU, and because I don't see any errors here, we can check if, yeah, it played one episode. So I think my code is working. So I right now will stop the build, cancel build, and I'll introduce you with the reward system. So firstly, let's plot our reward graph, and let's see how it changes when we implement it in a different way. Where's my replay function. So here I'll add a pylab plot similar as we did in reward system, and here I'll simply plot my discounted reward, and of course I can beside this plot my reward. So this will be simply a line minus, and here I will add a pylab plot of reward, self-reward, self-reward, and let's add the axis. So at x equal pylab GCA and ax dot grid as true, and let's show our pylab plot. Should be fine now, and let's see what we receive. For now, discounted is reward equal to reward, so let's build this and let's see how it works with one episode. As you can see, we didn't receive any score, so all the minuses we received. We can play another round to check what we received. It's the same. Let's check till we get at least one score, or maybe we won't receive even it because probably it can't play in this way. So okay, I'll cancel this build and let's move to our reward system. So in all policy gradient agents, one of the most important thing is how we work with reward. From reward function depends how good our model will be learning. So I can, for example, print my reward. So for example, I will write print from 200 to 250 and see how it will look. And as you can see, here we scored 3 times 1 score, and all other times there was 0. So not that great. And here you can see is my reward, and this is an example how our rewards looks in our Pong game. So the rewards are mostly 0, and sometimes we might see 1 or -1 in the list. This is because environment just gives us reward when the ball passes through us or through opponent. When ball passes our paddle, we lose and get -1 reward, and when the opponent fails to catch the ball, we win and get +1. If we train our network with this reward, it learns nothing because the reward is most of the time 0. In this case, the agent does not get feedback what is good or bad. Most gradients will become 0 because the reward multiplication is used in loss function. And environment reward is just when the ball passes through our paddle, so we score -1, or our opponent paddle, so we score +1. Now think about it. Our paddle moves up and down, hits the ball, and the ball travels to the left side of the screen. The opponent fails to catch it and we win and get a score of +1. In this scenario, which action were actually good? And the action we took when the ball hit the ball, or the action we took when we get score of 1? And of course, the first option is correct. The second option is wrong because the ball is reaching the opponent. Our action does not matter. Only the action that we took to hit the ball were important to winning, and everything after hitting the ball was irrelevant to our win. So a rather similar argument can be discussed about losing. The action near when we get score of -1 is more important than action taken many steps earlier. So we'll do here a trick. We set the reward of actions taken before each reward similar to the reward obtained. For example, if we got reward plus 1 at time 200, for example, we say that reward of time 199 is 0.99. So reward is reduced by 0.01, and similarly we'll do for second step and third and so on, which with this reward definition we have the reward for action that actually resulted in +1 and -1, and we assume the more recent the action for the reward gain, the more important it is. So we'll define here a discounted reward function that does this for us. Note that this might not be applicable in other environments, but serves our purposes for this game project. So for example, I'll write that, for example, at first I begin from my gamma. This will regulate our curve of increase or decrease, and earning at will be equal to 0, and of course we'll start with discounted reward, and it will be 0 in the same shape as reward. And here now we'll use our for loop. So for I in reversed range, we use reversed because we check all the rewards from the ending of episode, and here we go from 0 till the length of reward. So this is our first for loop. Next we check if our reward is not equal to 0, and if it's not equal we then calculate a running add. I mean, we not calculate it but zero it. This is Pong specific, I should write, and in other environments we won't use these two lines, so we simply would write something like running add equal to running add multiplied by gamma and plus reward of I. And here is the last step. So we use our discounted reward. It will be equal to our running add, just like that. And simply at the end of this whole loop we return a discounted reward. So right now we can check how it looks for us. So here, instead of this, I'll add a dot in a graph. So let's see. Something was wrong here probably. Try to run this on my CPU. Oh, I understood. Okay, this is zeros live I should use. So everything was here, there fine with GPU. Discounted reward is not defined. So as you can see, here is my plot. Here is the discounted reward plot, and here dots is as usual not discounted reward. So as you can see, where we lose, here is a -1, and where we win, as you can see, is +1. So furthermore, we are finding the function to subtract reward by mean and divide by standard deviation, and then we'll discuss the result. You'll see that it should be much better there than it is right now. So simply cancel build, and here what we do is that I use a discounted reward, and we subtract from it, we subtract numpy mean of same discounted reward, and then, as he said, I divide it by numpy standard deviation, and let's see what results we receive. Here it is, and so now we have rewards bigger than minus 0.9 most of the time. So as you can see, we never hit minus 1. The new score is about minus 0.9. As seen in this chart, steps before it also has negative rewards. The negativity of the reward goes down as we go to the left from each minus 0.9 score. Also, you can see that we got some positive scores in our new chart. This is because we subtracted by mean. Think about it, what it can result, and the positive reward happens. I will try another one. The positive reward happens in the long sequences of playing. These are situations where we catch the ball and didn't get a minus 1 immediately, but we lost later, for example. So here's another example. So setting a negative score is logical because we ended up getting a minus 1. As you can see here, setting a positive score could be justified by what we approve actions where we catch the ball and did not get minus 1 reward immediately. Maybe we didn't win either. So in some point you can see that even when we didn't receive a positive score, so this example, some hills are higher than other. This is because our agents succeeded to survive longer than usual. This also helps for learning. So now that we have defined our reward, we can go to the next step and start training a full network. As you can see, here we didn't receive a plus 1 score, but probably we catch the ball about 2 times maybe. So now I'll cancel a build, and I think we can simply change our function. We'll use this one where we sample our weights with discounted reward. We won't use this plot anymore because we would like to train our full agent, and simply let's run. I'm not using a render this time because without render it trains much faster, and let's see for a few steps what results we receive. And this was minus 21. Let's move. Not using my GPU, so I'll reboot this. As you know, reinforcement learning is impossible almost to train on CPU because it's resource hungry. Again, there is something that my GPU came. I'll try my first GPU. Yeah, it's working, and as you can see, I'm receiving most of the time minus 21, and I'm not sure why. Yeah, I got minus 20, so probably it's learning. So I'll come back later with our results. It might take a while to finish 1000 steps, so we don't want to sit here and watch how it's training. So I'll stop the recording and we'll see later. So I've finished training my long deterministic V4 model, and now I will show you a test results, what I received. Let's first run it. Play it for us a game in by side, and it's like a proof that it's working, because I'm not going to upload this to our GitHub because model takes too much space. So I'll simply show you the results, what I received. So here is the graph, and results you can see from this graph, from the training graph. We can see that our model reached average score of 20, somewhere around 700th step. It's quite nice. I also trained a Pong V4 model, V0, and right now you'll see the results, and it took much longer to train, and I trained it for 10,000 steps. I actually can show you the results. And from this graph we can see that our agent learned to play Pong, but it was very unstable. I thought it plays Pong much better than random agent, but testing this model would perform quite bad. Actually, I can run the test. I already have the name of it. I use the same model architecture, so let's run. And where's my image? As you can see, while it's playing, policy gradient model learned to play and score some points. I made our model of one deep layer because of simplicity. I didn't want to make perfect agent, but if you want, you can try and train the network a lot more so they can play better. You can try playing around with convolutional neural networks, but then you would need a discrete learning rate, decreased learning rate. But as a result, you will get smaller model. Because now model takes around 100 megabytes of size, so I can't upload training model to GitHub. But it's actually not really worth of it. Actually, it's better for you to try to implement by yourself and try to teach some kind of game to play for your computer. And to conclude this tutorial, I could say that from this tutorial, we face a problem because we only calculate the reward at the end of episode. We average all actions, even if some of the actions take it very bad. If our score is quite high, we will average all the actions as good. So to have a correct policy, we need a lot of samples, which results in slow learning. And you might ask how to improve our model. We'll see in the next tutorials. And I'll do some improvements in coming tutorials. So I will do two of them. I will implement an actor critic, a hybrid between value-based algorithm and policy-based algorithm. And my goal is to implement a proximal policy gradient algorithm, which ensures that the deviation from the previous policy stays relatively small. So actually this is my goal, and you'll see we'll reach my goal and we'll check what is the difference between policy gradient. So thank you all for watching. I hope this tutorial was useful for you, and actually you can see the score. I didn't expect it even that it will play so well. Probably we are using the model which was saved in this point, because this point has the highest average score. So actually I'm surprised. So anyway, I'm really happy that I implemented this. I will upload code to GitHub. You can fully download it, try to change the model architecture, or try to implement to different environment. So thank you all for watching. See you in our next tutorial.